is analogous to the classical bit, but it can exist in a superposition states. So it can be 0 and also it can be 1, and it has the ability to be partly in 0 and partly in 1. So if you map this on a superconducting circuit or an artificial atom, typically you would need two distinguishable and stable energy levels to represent 0 and 1 states, and the ability to manipulate and read out those states accurately. This was a breakthrough. It proved that a man-made circuit wasn't like a classical switch, like just 0 or on or off, but you can use it as an artificial atom with a ladder of specific energy levels. Hence, we understand the following. With this circuit, if you map the qubit on it, you will need the ground state of this artificial atom or the lowest energy to represent the qubit state 0, and the first excited state or the next level to represent the qubit state 1. And hence we can call this a superconducting qubit. Superconducting qubits are made of simple oscillator circuits consisting of capacitors and inductors. Then they are cooled to sub-millikelvin temperatures, where it makes it superconducting and electricity can flow without resistance. Then it would turn into a quantum system where energy levels are quantized, as I mentioned before. However, the spacing is even. With the additional Josephson junctions, for example, you can introduce nonlinearity and create discrete energy levels which are uneven. So you can control them easily, and you can focus on the lowest two energy levels to represent the 0 and 1 without touching other higher levels. And after this, you can control the circuit with microwave pulses to perform quantum operations and also read out the qubit state by sending microwave signals to a nearby resonator that is coupled to the qubit. With this Nobel Committee honors fantastic pioneering discovery of macroscopic quantum tunneling and the development of superconducting qubits, which are now a leading platform for building quantum computers. Of course, quantum computing is still in its infancy, and there are many challenges to overcome before we can build large-scale, fault-tolerant quantum computers. Such level would enable us of performing meaningful computations that surpass the capabilities of classical computers. For example, to perform chemistry simulations, you would need thousands of high-quality qubits with low error rates and long coherence times. And with these fault-tolerant quantum computers, we expect to be able to do such or some useful quantum computations beyond proof-of-concept use cases.